Okay, this is the first video in the second chapter. We are starting to describe location and what that location exactly means. We're going to start talking with percentiles and ogives. Our essential questions for the day are whether the differences between a percentile and a z-score, and how are ogives different from other graphical displays. So here is your AP Statistics standard. We are interpreting graphical displays, and we are summarizing those distributions, partially by measuring the position with quartiles, percentiles, and standardized scores. So keeping those essential questions in mind, let's start talking about percentiles. I know we've mentioned them before, especially when we talked about box plots, but specifically, a percentile is the value that has p% of observations less than or equal to it. So if I know a value in a distribution, its percentile is the percentage of values that are equal to or less than that value in the distribution. And in order to calculate that, you count up the numbers in your distribution that are less than that particular observation, and you divide it by the total number of observations. And it's a pretty simple calculation. So let's start by calculating percentiles. First, let's look at the percentiles for Barry Bonds and Hank Aaron. They're baseball players, and here we have a back-to-back stem plot that displays the number of home runs per year that each of them had, and this was for both of their careers. So Barry Bonds had 22 years in his career, and Hank Aaron had 23 years in his career. So and there's different time periods, so you should keep that in mind whenever you're comparing these distributions. So as we're comparing these distributions, I want to look at the times that Hank Aaron and Barry Bonds both hit 40 home runs in a year. So that happens right around here. In order to find out the percentile that they were at for their entire career by hitting 40 home runs in that year, we have to count up the number of values that were less than that. So for Hank Aaron, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 years in which he hit fewer than 40 home runs. So 15 out of his total 23 years puts a home run hitting year of 40 home runs at the 65th percentile for him. For Barry Bonds, I counted up the number of times that he hit fewer than, excuse me, that's an error. Hold on. Okay, it's been fixed. The number of times Barry Bonds recorded fewer than 40 home runs adds up to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 out of his 22 years, he recorded fewer than 40 home runs in a year. Thus, when he hit 40 home runs that year, he scored in the 64th percentile for his record of years batting home runs. Okay? So those are how you calculate percentiles. Now I'm going to talk to you about a z-score. A z-score allows you to basically standardize scores against one another. And the way we calculate a z-score is we take the x value that we're interested in, subtract the mean, and divide by the standard deviation. And the notation I'm going to give you is x minus mu divided by sigma. So that's your mean and your standard deviation. It tells us how many standard deviations of a particular value that x value is from the mean. So it doesn't have to be an exact number of standard deviations in terms of a whole number. It can be a decimal. So if it's possible, if it's positive, the value is above or greater than the mean. so it's to the right. If it's negative, then the value is below or less than the mean. The mean is the 50th percentile, and so above would be higher than that, and below would be lower than that. So your example is that Eleanor scores 680 on the mathematics portion of the SAT. And it gives you the distribution of the SAT scores with the mean 500 and the standard deviation 100. Gerald doesn't take the SAT, he takes the ACT. And in the mathematics section, he scores a 27. And the mean of those test takers was 18 and the standard deviation was 6. So what we want to do is compare the z-scores to one another to compare Eleanor to the entire population that we're taking the SAT, and Gerald to the entire population taking the ACT, and that allows us to compare them to one another to see who has the higher score. So I calculated the z-score. First, the z-score for Eleanor was 680. That was her score. Subtract 500, the mean, divide by 100, the standard deviation, which gave her a z-score of 1.80. I calculate z-scores to 2 decimal places, and you round appropriately. It was 1.8, but I put the 0 there just because z-scores kind of need to be calculated to 2 decimal places. You'll find this out later, unless you recall from knowing this before. Now I'm looking at Gerald. Gerald scored a 27, and so 27 subtract the mean of 18 divided by 6 standard deviation. It gave him a z-score of 1.50, 1.5. That means Gerald was 1.5 standard deviations above the mean, and Eleanor was 1.8 standard deviations above the mean. With that analysis, I would say that Eleanor did better on her mathematics score than Gerald, just because she scored better than 1.8 standard deviations to the right of the mean, whereas Gerald only reached 1.5 standard deviations above the mean with his score. So another example, we've got 3 baseball greats, Ty Cobb, Ted Williams, George Brett, and we're going to compare their batting averages. The thing is, they participated in the sport at different time periods. So even though I have Ty Cobb's batting average of .420 and Ted Williams of .406 and George Brett of .390, which one is truly better? We have to compare against the distribution of that time period. And here are the 3 different means based on the decades that they were in, and the 3 different standard deviations based on the decades that they were in. So what we're going to do is calculate the z-scores so that we can standardize and compare how far they stood not only above their peers, but compare them to each other slightly. Okay? So first, we have to calculate z-scores for each of the 3. Cobb's z-score, by taking his batting average minus the mean of that decade divided by the standard deviation of that decade, gave him a z-score of 4.15. So that's 4.15 standard deviations above the mean. Williams had a score of batting average of .406, and we subtract the mean and divide by the standard deviation of that time, and he has a z-score of 4.26 standard deviations above the mean, even higher. And Brett had a batting average of .390, subtract the mean of his decade, and divide by the standard deviation of his decade, and he ended up having a z-score of 4.07. So this is how high they stood above their peers, the other baseball players of their time. It appears that Williams has the best z-score here in terms of did the best amongst his peers in that decade for playing baseball with his batting average. Now let's talk about a relative frequency graph. This uses percents instead of counts. And we've constructed a relative frequency table. And the way we did so is by taking our frequency and dividing it by the total number of observations that we had and constructing percents. And we're going to start constructing what's called an ogive. And the ogive uses relative cumulative frequencies in its graph. It looks kind of like a line graph, but we'll do more with this tomorrow. These are the steps, and we will go into them tomorrow, but the things while we need to remember while we are constructing our ogive is that the graph is cumulative, so it's always increasing. And because of that always increasing attribute, it is always skewed left, okay, in terms of its shape. And that's going to be it for today. Please bring your book tomorrow, and we will finish this lesson on your sheet together. Bye.